When we're solving linear inequalities, there is one caveat, and that's going to be probably easiest to explain by just using an example. When I have 5 equals 5, everyone knows that that's true. 5 does equal 5. If I took 5 plus 1, then we knew that that equaled 5 plus 1. That was the addition property. We said, well, if we add 1 to the left, we have to add 1 to the right, and I'm going to get 6 equals 6. I also have the same property that says, hey, if you've got 5 and you take away 1, you have to take away 1 from the other side for 5 still to be equal to 5, and you're going to actually end up with 4 equals 4, but you still get that identity. Hanging on with that 5 equals 5, if I double both sides, I'm going to get 10 equals 10, and it was okay to double both sides. I could have gotten half of both sides. If I take half of both sides, I'm going to get 5 halves and 5 halves. Same thing goes true with inequalities. If I had 5 is less than 6, if you add 1 to both sides, it's still true. There's no problems there. If I took 1 away, there's still no problems. And also, if I doubled both sides, it's still true. Where the trouble comes in with inequalities is the concept that if I have 5 is less than 6 and I multiply, let's make it even better. Let's make it a negative 5 is less than 6. And what happens if I come along and I say let's multiply both sides by a negative 2? What I end up with over here is now a positive 10, and what I end up with over here is a negative 12. My previous symbol of being a less than is no longer true. Whenever you multiply or divide an inequality by a negative value, you must change your inequality symbol as you progress through the problem. Okay, so coming back to our examples, example 5, if we have 1/3 x equals 5, we have this equality property that says, hey, you know what? We can take, and I don't like that 1/3, so I'm going to multiply this side by 3 over 1, which means I'm going to multiply this side by 3 over 1, also just 3. So I end up with 3 over 3, which makes 1x is less than 15. All good from there. It's the set of all x's such that x is less than 15. That's going to be my solution set. I can put it on a graph without really too much trouble. Somewhere there's a 15, and I'm going to color the less thans, and I'm going to use the appropriate symbol. And based on that, I'm going to recognize that a negative infinity was being colored first, coming from my left. I stopped at 15 with a parenthesis, and so there's going to be my interval notation. The next example, we add a little problem here. I've got a negative 3x is less than 21, and what we have to do here is we've got to really be paying attention, because to isolate the x, we divide both sides, and what we end up with then is x is, I'm just going to leave the symbol out, and a negative 7. And it's the negative symbol on the division that makes us have to change this symbol around. So we no longer have a less than, we have a greater than. For exactly the same reasons that a negative 5 being less than 6, when we divide it by a negative 2 or times it by a negative 2, the symbol is going to change. So this is the key piece right here. Whenever you multiply or divide by negative, your inequality will change. I can use the solution set very quick, x such that x is greater than a negative 7. I can put it on a graph. I've got a negative 7 living somewhere, and I'm going to color the greater than side, and this was not non-inclusive, so we're going to go this way, color my arrow. Coming from the left, the first number that works is a negative 7, and it works until I get to infinity. And there we have our interval notation, our graph, and our solution set.